Hey everybody, welcome back. Today we're going to be talking about quantum search algorithms. Last time what we did is we talked about quantum query complexity and showed how we can use this as a lens in order to be able to study what the relative power of quantum to classical computers are. Before, we took a look at a toy example, specifically the Deutsch-Jozsa algorithm, which showed a super exponential separation in query complexity between quantum and classical computing for a kind of useless problem of determining whether or not a function is constant or balanced. So today we're going to be looking at an example that is actually much more practical, which is the example of quantum search. And to give you an idea where we're going to be staying on related topics to this for a while. What we're going to be doing is we're going to be beginning by talking about quantum search, and then its generalization in a technique known as amplitude amplification. We're going to then go and show the optimality of this algorithm by presenting to you a technique that can be used in order to be able to find loose but easy to derive lower bounds for quantum query complexity, known as the polynomial method. And with that, you'll have a very good idea about this tool, which is one of the most useful ones in quantum computing. So that's sort of where we're going. And a downside, though, that I'll have to warn you about beforehand is that quantum computing for this application of searching, unlike Deutsch-Jozsa, does not give a substantial speed up. It gives a substantial speed up, but does not give an exponential speed up relative to what we can do with classical computers. And I'm going to argue why that's actually to be expected from complexity theoretic arguments. So that's where we're going, and let's get started. So, quantum search. So let's take a look at the search problem, the classical search problem, from the perspective of query complexity. So the way that we can end up viewing the search problem is what we want to do is we want to be able to look for a particular set of bit strings. So for example, let's assume we have a function f. And what this function does is this function we can view as an oracle or a black box function. And what it's designed to do is it maps, from bit strings, say z2 to the n, maps to z2. And a query to f ends up saying like f of x equals 1 if x is marked and 0 otherwise. On the online version of this course, we took a look at the search problem in more detail in the previous recorded lecture. But this, I'm just going over this as review for those of you who've tuned into that. So otherwise, f of x is equal to 0. So that is the definition of our black box function over here. And what our aim for the quantum search problem is we want to find a y such that f of y equals 1. Okay? And ideally, we want to be able to do this with as few queries to f as possible, i.e., we want to be able to use f as few times as possible in order to be able to identify a single input such that f of y equals 1. Now, classically, we argued in the previous online recording that the classical number of queries needed to solve this problem is order 2 to the n. Okay? And with quantum queries, the question is, how much better can we do? Can we do order n? And the answer is a resounding no to this. I'll put 3 exclamation marks to emphasize how no this is. So, why, you might ask? Well, one of the reasons why we know that this is not going to give an exponential speedup, or is not likely to give an exponential speedup at the very least, is actually from computational complexity theory. So, I'll begin by showing you that argument, in part because it gives a good example of how I find I practically end up using computational complexity theory when I'm trying to devise quantum algorithms. It's very useful for me to have an idea about, roughly speaking, how hard particular problems are, because if we're trying to solve a hard problem with a quantum computer, it's very unlikely that we're going to be able to get an exponential speedup. So, the claim is, if an efficient quantum algorithm for search exists, then NP is a subset of BQP. Okay? Now, this statement is actually, at first glance, somewhat trivial, because what I'm saying is that if we can do quantum search efficiently on a classical quantum computer, then we can solve any problem in NP in polynomial time on a quantum computer. And in order to understand how that works, let's take a look at the proof. In order to be able to make this happen, what we need to do is we need to find an example of what's known as an NP complete problem. Okay, meaning that such a problem, it can be mapped into any problem in the class NP with at most polynomial overhead. So, taking a look at the lexicon of problems, the simplest example is examples of Boolean satisfiability problems, such as 3-sat. And the way that 3-sat ends up working is that 3-sat ends up taking, for example, a bit string x, which I'll call x1, x2, ... all the way down to xn. Okay, and what it tries to do is it tries to pick a function such that f of x is of the form, say, x1 or not x2 or x3 and x4 or x5 or x6, going all the way down. So basically what ends up happening is that this function is just the AND of a bitwise group of ORs between the individual bits, with occasionally negations thrown in between them. And what we want to be able to do for this problem is we want to be able to identify a bit string y such that f of y equals 1 for something like this. And this problem, by the Cook-Levin theorem, is NP complete. Furthermore, once we write it like this, it's clear that this problem is a search problem, because our goal is to be able to find a value of y such that f of y, which in this case is a efficiently computable polynomial or efficiently computable function. This is an example of a search problem, and therefore, if we can solve a search problem, if search is efficient, then so is 3-sat. And this implies so is every problem in the complexity class NP. And therefore, efficient quantum algorithms exist for this if and only if NP is a subset of BQP. All right. Now, this is strong evidence suggesting that quantum computers are not going to be able to provide speedups for this problem, because if you recall the way that the arrangement of complexity classes ends up going, where this is BPP, which is the class of all decision problems that can be efficiently solved in a probabilistic Turing machine. BQP is outside of it, and NP is conjectured to kind of, at least in this distorted rendition of the complexity classes, look kind of like that. So it's widely believed that there are some problems in NP which sit outside of BQP. And so for that reason, we strongly suspect that BQP is distinct, and in turn, this is evidence that that an efficient algorithm doesn't exist. But ideally, we'd like to be able to build up kind of a more detailed argument. Well, why is it that such an algorithm is unlikely to exist? And can we take a look at the structure of the problem in order to be able to provide more concrete arguments of why this is unlikely? And search gives us such an example, because since search ends up causing this reduction, if we take a look at it through the lens of query complexity, we can actually prove something much more concrete. What we can do is the ultimate claim that we'd like to make is claim there exists a quantum algorithm that runs, or that solves search using order root 2 to the n, or in general, let's change this to capital N, queries. Whereas classically, omega of n queries are needed. Meaning, where this omega is just like big O, but it means lower bounded. So that is the gist of what we want to show. And a further corollary that we're going to prove later is that there exists a quantum algorithm that is optimal uses big O, well, let's call it big theta square root n quantum queries to F. Okay, so again, the proof of this corollary is that this algorithm is essentially optimal is going to have to wait until we can spend some time looking at the polynomial method in a couple of lectures. But showing the square root n speed is actually relatively straightforward, and it can be reasoned out strictly using geometric arguments. So, proof of claim. Okay, the way we're going to prove this claim is, fortunately, the proof is constructive. So we're going to begin by thinking about how we're going to do it. So the intuition behind this is that we need to start with an initial state that represents our prior knowledge. So our algorithm is going to begin with first step, initialize quantum state. Now, we know nothing about marked state. Except, you know what, let's just say without loss of generality, I'm going to call the marked state that we're searching for M. I'm going to also assume in here, just for this discussion, that the marked state is unique. Now, once we've talked about amplitude amplification, it'll be clear how to easily generalize all of this to non-unique marked states. But let's just focus on the simplest possible case first. Okay, so we're going to focus on the case where M is unique. And now, assume that what we have is we also have access to an oracle, a unitary oracle, OF, that will actually compute this search function. So for example, OF acting on x and 0 is equal to x 1 if x equals m and x0 otherwise. So this bit over here, this one stores the a bit that records whether marked or not. Okay, so that's the basic idea behind this. So OF implicitly kind of knows what our state is, because again it will map M0 to be M1. So if we're lucky enough to just guess what M is, then we can actually do this in one query. But it's not likely we're going to guess right the first time, especially if there's 2 to the n items. So the thing that makes the most sense is to initialize, given all of these things, our quantum state to a uniform distribution over all the values of M. Because if we don't know what the right answer is, we don't want to bias ourselves incorrectly in the wrong direction. So in that case, what we do is we prepare an initial state, psi naught, which is just going to be Hadamard tensor n acting on 0, which we can write as 1 over square root 2 to the n, sum over j. Okay, great. So first step is we begin by preparing a uniform superposition over all states. The second step is what we do is we iterate reflection operator This reflection operator is often known as a Grover iteration. It also is sometimes called the Grover walk operator. But in any case, the idea behind it is that what we want to do is we want to begin with by defining a reflection operator. So I'm going to call this reflection operator W, and I'm going to write it out in a kind of mysterious way. But I'll spend some time in order to explain what's going on and why this ends up working. So I'm going to put a negative sign here and say this is identity minus psi naught times identity, oh, sorry, it should be a 2 there, minus 2 m. All right, so what is this saying? Each of these operations over here is what we call a reflection. Now, why are these called reflections? Well, let's take a look at the simplest case, right? The simplest case is, let's say, identity minus 2, 0, 0. The matrix representation for this guy is the following. It'll be a minus 1 up here, and then everything else will just get mapped to 1. You can see that because if you plug in 0 over here, you'll end up getting I 0 minus 2, 0, 0, acting on 0. Okay, which ends up giving you minus 0. So that's where the minus sign ends up coming from in this expression. So we've got the minus sign there. Now, the next question is, okay, well, what does this actually mean? Well, if we've got a vector v, and I'm going to draw this vector out in the following way. We can always end up seeing v as having some component in the 0 direction and some component in a perpendicular direction over here. And v will be pointing maybe out there. Okay, what this reflection is going to do is it will take v, which I'll write as some arbitrary angle sine theta 0 plus cosine theta perpendicular. And I can do this always because of the fact that the vector has to be normalized, and this is clearly an arbitrary unit norm state. So if we have this, then we apply this operator to it. Then, because 0 goes to minus 0, but everything else remains 1, this is going to map to minus sine theta 0 plus cosine theta perpendicular. So maybe actually this wasn't the best example for me to do, but what will happen in this diagram is the component parallel to 0 flips directions. So our vector v is going to get flipped around to this side over here. And from this perspective, you can see that it just ends up implementing a reflection of the vector about the a plane perpendicular to the 0 axis. Okay, so that is entirely what this ends up doing, and that's why we call it reflections. Similarly, this reflection operator does a reflection not about 0 but about m. So if our vector was of the form, I don't know, sine theta m plus cosine theta perpendicular, this would end up going to, again, minus sine theta m plus cosine theta perpendicular. And the same thing ends up happening with that reflection. So that's what this walk operator does. All right, so in order to understand how this ends up scaling, let's actually just take a look at our initial state. Our initial state is psi naught. And if we were to just begin with the dumbest version of the algorithm and ask, okay, well, if we were to measure this right away, what would be the probability of us getting 0? Recall that psi naught is a uniform superposition over all states. So it's the sum of j over here with 1 over root 2 to the m. So our probability of getting m when we measure it is just going to be equal to 1 over 2 to the n, sum over j, inner product with 0 and j, absolute value squared. Because the probability of getting a, sorry, it said 0 over here, I mean m. Because the probability is just the inner product squared. So, in this particular case, this is actually just equal to 1 over 2 to the n. And we, of course, expected that completely because of the fact that this is a uniform distribution. So all items are equally likely, so the probability is 1 over 2 to the n. Okay. Here, what I'm doing is I'll be sticking with the fact that there's 2 to the capital N, the number of items, is 2 to the n. Later on, it'll be convenient for me to assume that we've got a different number, but for the moment, let's just pretend that we've got a power of 2 different ones. So that way we can visualize the circuits a little easier. So that would give us the probability. Okay, so we can start out with this, but I'm going to actually try to use this representation over here. So using this representation, I can always write psi naught as sine theta 0 plus some perpendicular vector. Okay, well, that's not too surprising, but the angle theta, if we end up doing this, because the probability squared is 1 over 2 to the n, this has to satisfy that sine squared theta is equal to 1 over 2 to the n. And this implies that theta has to be equal to the arc sine of 1 over square root 2 to the n. Okay, so this is the angle that we begin the algorithm with. So if we look at what's happening with the algorithm, again, we're applying psi naught goes to this walk operator, W times psi naught. And this is basically W equals negative identity minus 2 psi naught times identity minus 2 m. Okay, and we've assumed, oh, I'm sorry, I said 0. Some part of me just really wants the mark state to be 0. We've picked it to be m. Okay, so that's what this does. So this carries out a pair of 2 reflections. Now, drawing the diagram, if we pick this basis, let's put m up here, and this over here I'm going to call perpendicular, and our initial vector, psi naught, is pointed up in this direction over here. Okay, and this angle down here is going to be theta geometrically. Okay, so what we're going to do is the very first step we do is we carry out this operation. Now, as mentioned before, what this operation does is it flips the component of the vector pointed in the m direction. So it does a reflection about this axis. So, reflecting about that axis, we end up translating to a state down here. Okay. Next, what we do is we reflect this vector about the original state. And that ends up coming from the minus sign. So we're not reflecting about the space orthogonal to the initial state, because the minus sign makes it a reflection about the initial state. So when we do that, Note that this angle over here is 2 theta. So when we turn this back, we're going to get an angle of 2 theta up here. So just from the geometry, all that ends up happening from this transformation is W sine naught is just going to be sine of 3 theta m plus cosine of 3 theta perpendicular. You might wonder, where's the 3 coming from? Well, the reason why is because this process added an angle of 2 theta to it, but we still had this angle of theta here. So if we want to consider our angle from the perpendicular vector down here, that total angle is 3 theta, which is why that's a 3 theta here. But the key point is W maps theta to theta plus 2 theta. Okay, so in general, if we ended up applying W to the P to our initial state, psi 0, this is going to give us sine of 2 theta, or sorry, 2p plus 1 theta m plus cosine of 2p plus 1 theta perpendicular. All right, so that is what we end up getting out of this, and we can actually see pretty quickly where this ends up coming from, or how this ends up giving a quadratic speedup. But I want to take a step back and actually just look at a particular case, or get some intuition for what's going on here. So what's happening is that we've got this vector that we're rotating about the axis. If we stopped here at 2 theta, we'd have a very high probability of success. But if we did one more, our probability of success would start going down. So if we continued this process, eventually this vector is going to start wrapping around the unit circle again and again and again. So how do you figure out what's the right value of P to pick? Well, the answer is actually kind of straightforward. Let's look at the simplest possible case, which is n equals 2. In the case where n equals 2, what we have is the number of states, which we've assumed is a power of 2, is 4. Okay? So, therefore, theta which is equal to the arc sine of the square root of 1 over 2 to the n, that is equal to the arc sine of square root 1 over 4. Okay? Which is equal, once you go through all the special formulas, that's pi by 6. So, therefore, W, acting on P in this case for psi naught, is going to be equal to sine of 2p plus 1 pi by 6 m plus cosine 2p plus 1 pi over 6 perpendicular. Now, let's take P equals 1. If P equals 1, then this ends up going to sine pi by 2 m plus cosine pi by 2 perpendicular, which is just equal to the m vector. And this implies that the probability of measuring m now is equal to 1. So, by taking advantage of the fact that we know what the success probability is for this case, we can compute the value of P such that the success probability is maximized. So, similarly, what we want to do is we want to be able to, in general, if we have our success probability, which is sine squared of 2p plus 1 of the arc sine of 1 over square root of 2 to the n over here. Then all we have to do is note that in the limit where n goes to infinity, what we can always do is we can always end up picking this to be pi by 2 plus minus some constant. If it's pi by 2 plus minus some constant, then our probability of success is going to be, about 1. It might be as low as 1/3. It might be as high as, 1. But regardless, even if our success probability is low, we would need only a few trials with high probability to make this work. In fact, by the Chernoff bound, a logarithmic number of trials would be needed in order to be able to get this to succeed with high probability. And in fact, on average, a constant number of trials will be enough in order to make this work. So on average, we only would require that many. However, in principle, actually, we can boost the success probability to 100% always, but I'll get to that later. So for now, it suffices to see that we can always make the probability of success arbitrarily high just by choosing for any fixed value of n, the value of p that makes this maximally close to pi by 2. And then if we can't quite make pi by 2, at least at this point, we'll just suck it up and eat some probability of failure. But that's not going to be too bad because it'll just be a small shift because this value over here is, going to be tiny. So if that's the case, basically what we really want is to get an idea of the asymptotics. If 2 to the n is much, much bigger than 1, we can end up using the approximation that arc sine of x is about x for small inputs. So therefore, this is about sine squared of 2p plus 1 over root 2 to the n. And this means that we've got to pick 2p to be roughly square root of 2 to the n, which means that p is in order root 2 to the n. Where what is p? P is the number of times w must be applied. Okay, so what this ends up saying is that if we can implement w, and if the number of times that we have to query the function f to implement this object w is a constant, then we can iterate in order to be able to get high success probability using a number of repetitions of these two reflections that ends up scaling like square root of the number of entries that we're searching, not linearly like the classical lower bound. Okay, so that gives us the number of times that w has to be applied, but we need to be able to, as I said, relate this to the number of oracle queries. So the next step is the oracle decomposition. So if you recall, w is of course equal to minus identity minus twice the projection onto the initial state multiplied by identity minus twice the projection onto the marked state, m. And so you might ask, how do I carry out these things? And especially the second term, because it seems at first glance like you would have to know what the value of the marked state was in order to be able to implement this reflection. But fortunately, we can use our function OF to be able to do this. And how can we do this? Recall that OF acting on a state x and 0 ends up yielding a state x and f of x over here, where f of x equals 1 if x equals m, and 0 otherwise. Okay? Or, if you prefer, delta x, or f of x is equal to Kronecker delta of xm. All right, so this is our oracle function. So let's take a look at what a circuit for it might look like. Well, first off, actually, let's not quite worry about that at the moment. What we want to do is we want to do something very similar to this. What we want to do is we want to, instead of getting m going to m1, let's put a 0, we want m goes to minus m. And any perpendicular vector goes to the perpendicular vector back. Okay, so how are we going to do this? Well, the easiest way to do this from the perspective of the circuit is to begin with an input x up here and an ancillary qubit that I'm going to begin in the state 0 over here. Now I'm going to end up calling OF. This state over here is going to come out as x because OF doesn't change that input. However, down here, it's going to have the function value, i.e. it's going to have 1 if the input x is an item that we're searching for. Now, we want to be able to kick back this minus phase if this value of f of x is 1, i.e. if x is the same thing as m. And so we can do that by just putting a poly z gate in here. Because if f of x is equal to 1, then poly z acting on f of x is equal to -1 to the f of x over here, using some of the reasoning we did last lecture. However, this does the right thing. It'll put a minus sign out in front of the m, but unfortunately it'll flip this bit, so we need to unflip it down here with another instance of OF. And this circuit will formally end up mapping the state m0 to minus m0, and the state anything perpendicular to m and 0 to that perpendicular result, n0. So you can see that this has exactly the structure that we need. Okay, so this circuit ends up implementing that reflection. And note, we don't need to explicitly know what the value of m is. We only need to implicitly know m inside OF. So somehow, either in the code or in the properties of the oracle, it's obscuring the fact that m is in here. So we don't need to know it. The subroutine just implicitly have it. So that's how we get around the problem. Now, the next question is, how do we do the reflection about the axis perpendicular to psi naught? So that part, to some extent, is a bit of a red herring, if you think about it, because we're most interested, for the purposes of this argument, in quantum query complexity. And the number of queries that we're going to need in order to be able to implement that reflection operator is 0. The reason why is because of the fact that psi naught doesn't depend on the value of m. It doesn't depend on the oracle. And so no quantum queries are going to be required in order to implement this. But it's useful to see this, so I'm going to spend a little bit of time talking about how we would build a circuit for this, so you can see what the entire Grover algorithm is going to look like. So let's consider building a circuit for the following reflection operator: I minus twice 0 tensor n, 0 tensor n. So again, this is of the form -1, 1, 1. Okay. And so the matrix can actually be carried out in the following way. We can see that if our inputs, if we do the following, or sorry, if I take a look at the gate, maximally controlled top Z down here, this circuit actually is very similar, but it has the opposite pattern. Unless all of the bits are 1, then you don't get a minus sign. But if all of them are 1, we do. So we want to switch this around. We want it to make it so that when all of the bits are 0, you should get a minus sign. So what we're going to do is we're just going to flip every bit before and after. Okay? So this circuit will transform 0 into 1 and 1 into 0, and thus turn this into that. Also, because I'm going to have to draw this circuit over and over again, I'm going to use the notation that x conjugated around a control is drawn by a 0, or an empty circle up here. This again isn't just another way of saying that this circuit triggers when the bit is 0, not when the bit is 1. Okay, so this circuit can be written in the form which is the simplest way I know within our notation to represent this. Okay, cool. So now we've found this one particular reflection, but that's not what we want. We want to figure out how to do the reflection 1 minus 2 psi naught, psi naught. But recall that psi naught is equal to Hadamard tensor n acting on 0 because it's a uniform superposition over all the different values. So in that case, what we have is we have that this circuit actually can be expressed as, well, identity minus 2 Hadamard tensor n 0, 0 Hadamard tensor n. And here I've just used the fact that Hadamard dagger is equal to Hadamard. So that's why there's no daggers on this one over here. However, we have that H tensor n identity H tensor n is equal to identity. The reason why is because the identity operation, it doesn't do anything. So we could just remove it from all consideration. Those two cancel, and we end up getting the identity. So I can write this as Hadamard tensor n, identity, Hadamard tensor n, minus twice Hadamard tensor n, projector onto 0, Hadamard tensor n. Okay, cool, but now I can factor out the Hadamard tensor n's at the beginning and the end of the quantum circuit. And so this over here is the same as Hadamard tensor n, identity minus twice, projector onto 0, Hadamard tensor n. And so, and the quantum circuit, therefore, for this, just looking at the above diagram, is H, 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 X, Z, H, 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 H. Okay. And so formally then, our circuit that implements the walk operator, because it's just the product of this and the reflection that we just wrote, we can end up writing the whole circuit in the following way. We can write it as all of these guys end up going into this over here, OF, Z, OF. Let's just link all of these guys up. Here we go. And this is how we can implement the walk operator. So each walk operator from this part, which again is just an incredibly messy redrawing or attempt for me to redraw this guy over here. Each W has two applications of OF, which implies that order 1 queries, i.e. accesses or applications of the black box function OF are needed per W. Now, we showed previously that order 2 square root 2 to the n applications of W are needed to solve, or are sufficient, I should say more accurately, to solve the search problem. And because each one requires order 1 queries, therefore, order 2 to the n queries are sufficient to solve search. Okay, and so this shows that there exists a quantum algorithm that can give a quadratic reduction in the number of queries. And while that's not the same thing as an exponential reduction, it's pretty substantial, and it, in some sense, is kind of surprising. So what, if we had an unsorted database, for example, with 1 million entries, okay, then roughly speaking, if we wanted to do this with a classical computer, we would need to go through, well, 1 million minus 1 in order to be able to find the location of the marked element in a worst case scenario. Quantumly, we would only need to actually check 1,000 locations queries in superposition to do the same job. All right? And in effect, you might ask, okay, well, why is it a quadratic speedup? What feature of quantum is giving us this advantage? And so intuitively, let's just take a step back at the diagram that I gave for amplitude amplification, or sorry, for Grover's search over here. The diagram shows that every walk operator we do is doing a rotation in a 2D space, which is increasing the angle by p. However, the probability that we get the marked state ends up going like the square of the angle, i.e. this ends up going kind of like p squared theta squared. So what this ends up meaning is that for every operation that we do, we actually get quadratically more bang for our buck by doing it using quantum operations than classical, simply because of the fact that probability is equal to like the wave function, wave function's amplitude squared. Okay, like P of m is equal to the component of m squared. So it's this quadratic difference between amplitude and probability that allows quantum to do this actually much more powerfully. And that's exactly what we're taking advantage of here. And exactly why we get a quadratic speedup. And this, in some cases, can give us actually a pretty substantial advantage. So next time, what I'm going to do is I'm going to spend a little bit of time talking about how we can end up viewing this through a broader lens. I'm going to take a look at what the eigenvalues and the eigenvectors are of the walk operator, and actually its generalization to this concept known as amplitude amplification, which unfortunately you won't find in Nielsen and Chuang, because actually the idea came out in the year 2000, which was when Nielsen and Chuang was originally published. But nonetheless, this is one of the most important forms of a quantum speedup. It's been looked at repeatedly in quantum machine learning for speedups. It's been examined in cryptography for attacks on lattice-based crypto systems. And in fact, actually, it can also be used, as we'll see later, in order to give us a quadratic speedup for estimating probabilities. So these are reasons why this search algorithm and its generalization to amplitude amplification are so vital as techniques. So unlike the last oracular separation we looked at in the form of the Deutsch-Jozsa algorithm, quantum search is actually a very, very useful paradigm that can be tacked on top of other problems, in some cases even problems that give exponential speedups, in order to further optimize the algorithms. So that's one of the reasons why we should care about these problems, and its relevance is pretty clear already, because what this means is that if we have to resort to a brute force algorithm for solving NP-hard problems, just like we showed with the original search reduction of 3-SAT to search, then what we can do here is we can provide similar quadratic advantages for any algorithm in for solving NP-hard or complete problems that doesn't take advantage of the structure of the problem space. So that's why I think these algorithms are super cool, and why this will actually end up forming the basis for a lot of our subsequent discussions. Well, thank you very much, and I will see you all next time.